We just finished correcting our naive Gaussian reduction system by introducing partial pivoting. And partial pivoting went a long ways in protecting our algorithm from data-generated problems. Unfortunately, it didn't cover everything. It certainly covered the situation where we had small numbers that were causing us a lot of trouble in the system. We're now going to look at what happens under certain misplaced or certain problematic locations for big numbers. So we are going to define now a number called C. C is going to be a big number, like bigger than 10 to the 7th. Here's what our matrix looks like. We have the first row, which is really huge compared to the second row. But a solution does exist. Take the determinant and you'll see the determinant's equal to minus C. So we should be able to solve this thing. Well, let's go ahead and solve it theoretically. Here's our formula that we have for using the determinant and using the inverse. And we end up with this solution over here on the right. Now, what will the computer do with those expressions? Well, just like we had in with the really small numbers, if you compare two numbers that are quite different from each other, they're out of reach from each other with respect to the mantissa, and something's going to get swamped. You know, the 2 is going to get swamped out by the 2c, and that difference will just look like minus 2c. The same thing's going to happen with 4 minus 2c. The 4 will get swamped out by the minus 2c, and you won't be able to see the difference. Now that in itself isn't a big deal because numerically that's close enough. It will create some problems under some circumstances. If we take what we now consider the floating point version of that solution, and we'll get some cancellation, and we'll end up getting the solution 1, 1. Now let's look at the same problem in a little bit different way, again using a big value of C, and we will use the triangularization process with partial pivoting and see what happens. Here's the same system, my A augmented with B, and I need to first reorder these rows to guarantee that what's in the upper left-hand corner is the largest value in the column. Well, I've already got that. 2 is bigger than 1, and so I don't need to do any pivoting to make this thing consistent with the partial pivoting procedure. I do my Gaussian reduction. I get this 0 here in the lower left-hand corner, which makes this system now triangular. I can solve this using back substitution by just taking 1 minus c times x2 and setting it equal to 2 minus c. I do need to do that using floating point arithmetic though. So when I take 1 minus c in floating point, it looks like minus c, and I take the floating point of 2 minus c, and it looks also like minus c, which means my x2 will be calculated in the computer as 1 through back substitution. That's fine. That's what we got before. So now we simply stick x2 back into the system, use row 1 to calculate what x1 was. Here's the linear combination of interest. We need to work in floating point. So now we end up with 2x1 plus 2 times c equals 2 times c. Well, the two c's are going to cancel. I end up with 2x1 equals 0, and I end up with a solution of x1 equals 0. Wrong answer using our partial pivoting approach. So I need to be able to fix that with a new procedure, or maybe a slightly revised procedure. What we're going to do is now introduce something called scaled partial pivoting. We will take a little bit of advantage of the structure of the whole matrix, not looking at just the column alone. So here is a larger example to make this thing a little more obvious of what we're doing. And what we want to do is a procedure much like the partial pivoting, but with a little bit more protection. If I had done partial pivoting alone, this 12 would appear in the A11 position because it is the biggest in magnitude amongst the other players. We're going to do something a little different here. We're going to look at the value with the largest magnitude for each row. So in row 1, 13 has the largest magnitude, and I am going to set it off to the side. 18 is the largest magnitude in row 2, and I write it here. 6 in row 3, and 12 in row 4. And I make a little vector called S that will keep track of the largest absolute values in each row. This vector is going to be used throughout the rest of the algorithm. I'm not going to revise this as the algorithm proceeds, but I'm just going to save this S vector for use later. Now let's go ahead and go after the partial pivoting, but we will scale the values in each column first. This vector S will be useful throughout the whole algorithm. You'll see how that works in a minute. We will not change that once we start the procedure. What we will do is when we look at each column, we will scale the values by its applicable maximum. What do I mean by that? Well, we pulled 3, 6, 6, and 12 from the first column, and we will divide those values by the appropriate S entry, 13, 18, 6, and 12. Once we take those ratios and store them, instead of looking at the values in the columns themselves, we're going to look at the maximum scaled values. And we're going to call this the ratio vector. Once we determine which is the biggest scaled value, that will be the row that we will use to swap. So in this case, our pivot row is 3. You might complain and say, why didn't you use 4? Well, it's kind of arbitrary which one you use, so we use the first one that you come across. So now we will exchange row 1 with row 3. If we'd used partial pivoting, we would have simply looked at the maximum value in column 1 and found a 12, and we would have swapped row 4 with row 1. In this case, when we check the scaled values, the first maximum value, in other words, look at the max and take the earliest one we come to, is row 3. And so what we will be doing is swapping row 3 with row 1. Rather than using the maximum value of 12, we end up using only a 6. So when that swapping occurs, the matrix looks like this over here. Now we will continue with the normal row reduction that we have done throughout this entire algorithm. So here's our appropriate combination of rows that lead towards putting zeros in the first column, and that completes step 1. Then we will repeat all of that on the portion of the matrix that is one dimension smaller, in other words, the 3 by 3 in this case. But don't revise your S values. You will continue to use the same S vector as we go. So let's just take a look at how that works. So S was this vector here that we had before. We're only going to use the last 3 values because that's what's applicable to this 3 by 3. And we'll form the second scaled column by taking each of the entries in column 2, excluding the first row because we're done with the first row, and divide by the maximum values. So the values were 2, 12, and 4 in rows 2 through 4 of the matrix, and we divide by the maximums 18, 6, and 12. And when I say maximum, remember I mean maximum in absolute value. That gives us new ratios. We're only interested in the last 3 because that's the portion of the matrix we're using, and it looks like row 3 is the largest value of 2.0. So that means we're going to swap positions. We're going to swap row 2 and row 3. Let's take a look at the summary of the results. So here's my S matrix. Here are the ratio vectors that we used on the first column, and here are the ratio vectors now that we're using on the second column. So 2.0 is the one of interest in the second column, and we're ready to do some more row reductions. We first are going to swap row 2 and row 3, as you can see we've done here, and then we'll do the ordinary elementary row operations that will eliminate these coefficients and place in zeros, as you see down below. Okay, so now we just have one more step. Here's our third iteration as we're coming into the third column. As usual, we retain the original S vector. We calculate the ratios now just for rows 3 and 4, since those are the 2 that we're looking at. We discover that row 3 is numerically larger than row 4, so no swap is needed. We just continue on. Let's do the row reduction. That brings us to a final triangular form. and we are now ready to do back substitution. Okay, so as far as our back substitution is concerned, we'll use the same procedure we did earlier back in section 2.1. There's no change there we need to do whatsoever. Reminding ourselves of what our algorithm is, we are rearranging the rows first so that our scaled value is a maximum. We swap the rows that produce the largest scaled value in the diagonal, and then we triangularize in the same way we did with 2.1. Once the scaled pivoting is complete, you don't need to worry about any diagonal elements being 0, unless of course the system was singular to begin with, and we deliver our upper triangular matrix, all prepared for the normal backwards substitution. So we're now ready to work homework 2.2b. What I want you to do is go back to 2.2a and copy and revise it to form 2.2b. You're going to use the scaled pivoting using the maximum ratio method, swap the rows as you should using that scaled vector, and read in the same matrix and vector as you did in file a2.xl. Calculate the flops, and that'll all worth 20 points. And there's some additional output there that you may wish to look at. I will be running your code as usual to compare your values with mine. And those, you got a list there of the things that need to be performed. So with that, we will end this section off, and we'll switch gears a little bit on 2.2d. We'll still make some changes, but the changes will gain efficiency. And we'll save that till next time.